In this lesson, when we're talking about volume and integrals and how they're related, what I want you to see is that this is sort of some weird 3D function S, okay? It's just labeled S there, and we've got some kind of three-dimensional, looks like a shape of a bone or something like that. And we know, right, we know this. We know that a square, okay, this is a square right here, we know that a square can have an area, right? If it's in terms of x here, we can have find an area pretty quick. The formula for finding area would be x squared, right? But if we had a different shape, we had now a three-dimensional shape, and it turned out to be a cube. Bear with me as I draw this cube. If it turned out to be a cube with x and x and x, I could find the volume, and that would be x times x times x. Right? I guess I need another x up there. Now, how did we do that? We took the area of the original square, right here, and we multiplied it by the third dimension. So if you wanted to find the area of this thing, this S thing, one way you could think about it is to find the area of a slice and then find the area of another slice and then find the area of another slice until you have all of the slices accounted for and add them up. Now this is an irregular area, right? This is a cube. This is pretty easy. This one, not so easy because it's an irregular shape, okay? But if you think about this, how do we express, or how could we express changing areas of very small slices of three-dimensional objects? Okay, Riemann sums, yeah, okay, we've done that before. But how do we get exact without underestimating or overestimating? What is that called? It's called the integral. Now the area, if we knew what this function was, the area of this function would be the integral, okay? And the volume would be the area times a certain width, right? So if you recall, integrals have some kind of function, and I'll just put a of x here, and then it has d of x as well, right? Right? And so what this means is a collection of areas, but we also have this d of x here, so it's the area times a small sliver, right? Which really is volume. So integrals can be interpreted as a volume. Here's the area, and here is the sort of width of this small cross section. Okay, it's a small width, or the third dimension, whatever that is. Length, width. This would be height then, right? So this is a blown up picture of it, and obviously, if we took this as a regular shape where the both ends were exactly the same, right? Then we would be estimating a little bit here, but even though it changes shape, so you see how this is the actual shape because it kind of thins out. It sort of gets a little thinner here. Hard to draw that, but you see there's an overestimation here. But what happens if we bring this width closer and closer together? Then it gets more accurate, we overcount less. And so the integral, we take the area of an infinitely small slice and we add up those slices that are close to an infinite number of them. That's what the integral can do for us. All right? So let's take a look at this first basic example here. It's from the textbook. Okay, and this is what it says. It says a pyramid 3 meters high has congruent triangular sides. So here's a picture of the pyramid. Now we have this pyramid tilted on its side, and we'll explain why that might be in a second. It has a square base. Okay, so here's the square base, and that square base is 3 by 3 square base. Each cross section of the pyramid parallel to the base is a square. So what they're saying is, and I'll draw the pyramid for you upright if you wish, but this is the pyramid, and every section as we move up, so here's moving up a little bit, every section that you could draw would be another square, albeit a smaller and smaller and smaller square. You see that? So these are still squares, but we're getting super duper small. Everyone see that? And so we have a big square at the bottom, and then we have successively smaller squares until we get to virtually nothing, the tip at the top. Okay? Okay, so it says find the volume of the pyramid. Well, if you want, now we know a formula, right, for volume of a pyramid, right? It's length times width times height over 3. That's the volume of the pyramid, but let's say we didn't know that, or we wanted to use calculus to find this. What we could do is we could envision this pyramid as a successive number of squares, okay? And if we put this sort of in integral notation, we have the area of such square times an infinitely small sliver width. And if we added them all up, the sum sign, if we added up all of those little squares successively, we would get the area of the pyramid. The only problem is, or the only thing left to do, is to find out, hey, where do I want to start this whole process and where do I want to end, right? The limits of integration here. So, what might we do there? We have to have some kind of, limits of integration. Well, the area, let's do the area first. What's the area of a square? That's going to be x squared. So we will use this x squared. So we'll say x here by x and so on. That's the area of the square, x squared, that's fine. It's dx, so we got to use x. But now, where do we, again, let's get back to these limits of integration. So the reason why this pyramid is laid on its side like that is, I guess, so that you could see that we have area of the pyramid. If you tilt your head sideways, the area would be the base, and then we would want to go from the bottom of the pyramid all the way up to the tippy top, right? And so if we're taking these little slices and we're adding them all up, then you have to consider one end of the pyramid and the other end of the pyramid. So that's why it's tipped onto the side, so you can kind of see, all right, this is the area, and then we have other areas here, and where are we going to start and where are we going to end? In this case, if you start at 0 and you do this all the way up to what? Well, until you get to the height of the pyramid, which would be 3. So does it make sense that we go from 0 to 3 here? Okay. I know the x, this is the x-axis, but this is more the height of the pyramid, so that's what's a little strange about this. But hopefully you can see that we have the 2 dimensions, right? And then the third would be the limits of the integration. So we have the area, and then we have the limits of the integration. So, could we do this? Well, let's evaluate this by hand here. So we've got 0 to 3 of x squared dx. And so remember how we did this? What's the integral of x squared dx, or what's the antiderivative here? Yep, 1/3 x cubed, or x cubed over 3, right? Now, plus c, well, we're doing definite, so we don't have to worry about the c, but we're going to take this from 0 to 3. So how do we do that? Was that 1/3? Which one do I use? 0 or 3? Well, we do 3, yep, minus 1/3 times 0 cubed. And so what do we have? We have 3 cubed is 27 over 3 is 9 units cubed. Okay, so you see how we've got that? Now, let's go back and say we did remember our volume of a pyramid. That was 1/3 area of the base times the height. Do you remember that from like grade 10? Volume of a pyramid. So let's see, the area of the base is 3, what is it? The area of the base is 3 times 3 and the height is 3. So what's that? That is 1/3 9 times 3, and we should have 9 this way as well, units cubed. All right? So that is viewing volume, okay, as a collection, a summation of an infinite number of areas with small, small widths. And we just take all those little slices as thin as we can get, and we add them all up, and when you add up all of the areas in the third dimension, you get the volume.
So if you just know the function?
Yeah, you have to know, that's right, you have to know the function of the cross-sectional area in order to do this.
Then if you don't know, then you can't.
Well, if you don't know, I mean, if you don't know and you can't figure it out, then yeah, you can't do this, but you'll be given the you'll be able to find out what this cross sectional area would be, or the question will say, let's say this is a cone. Okay, so if it's cone, then what we have is we have a circle, right, to a point. So we have this cone happening, and if this was 3, you know what it means, or we could find the area of the cone the same way. This area would be the area of the circle. So we'd have pi r squared instead of x squared. And you'd go from 0 to 3, whatever the height of that cone would be. You would integrate this from 0 to 3, pi r squared or pi x squared, right? Whatever that is, and so on. Pi x squared dx, and you could integrate that.
Then you cannot calculate the first example that you gave us.
The first example, okay, so this one is just a picture of sort of what we're talking about. Yeah, there's no real question attached to this. If you were given some varying function here, if you were given some function of what this cross-sectional area would be, then yes, you could do it. But you'd have to be given the function. There's no example attached to this. This is just kind of concept. Yeah. Yeah, that's right. Okay. So if you know how to do this example 1 there, you're good for this cross-sectional area. Okay.